Step into any heavy industrial facility, and you are immediately confronted with thousands of complex machines running at once. Maintenance and reliability teams are responsible for managing everywhere from hundreds to thousands of these individual physical assets across an enormous footprint. Without a rigorous architecture in place, simply keeping track of where every single piece of equipment is physically located creates an immediate administrative crisis. Location is only the first variable. You also have to track the real-time physical condition, the operational parameters, and the complete maintenance history of each machine. To manage these thousands of moving variables at scale, organizations rely on a specific structural tool, the asset register. An asset register is a centralized database containing the exact technical and financial details for every physical asset owned by a company. It takes a sprawling physical landscape and maps it into a precise, relational, digital network. It serves as the definitive source of truth for the entire operation. An asset register serves a distinct purpose from a basic inventory of consumable parts. Inventory systems track supplies meant to be used up or sold. The asset register tracks long-term property, plant, and equipment that generate value over years. Inside a maintenance management system, the master data layer handles the static identifiers, the specific equipment tags, the designated locations, and the hierarchical relationships. The asset register extends that static master data by capturing every dynamic, transactional event that occurs throughout the equipment's lifespan. Master data gives the machine a name tag. The asset register records its operational DNA over decades of active service. Let's look at the complete life cycle data profile required for a single piece of high-value rotating equipment, like this compressor. The record begins in the planning phase, capturing the initial design specifications, manufacturer constraints, and operational requirements. Moving into the acquisition phase, the database logs the exact purchase date, the original capital cost, and the specific parameters needed for financial depreciation. Next is the operational phase, which explicitly stamps the date the equipment was officially commissioned and put into active service. From that day forward, every routine preventive maintenance task, lubrication cycle, and inspection result is appended to the asset's history. Any unexpected breakdowns, component failures, or major mechanical overhauls are also permanently etched into this profile. Finally, when the machine reaches the end of its life, the register documents its retirement date, its estimated salvage value, and the specific decommissioning details required for financial auditing. By capturing this uninterrupted end-to-end timeline, organizations can calculate accurate lifecycle costs and make mathematically sound decisions on whether it is cheaper to repair an aging machine or buy a new one. Collecting massive amounts of lifecycle data is useless without a standardized taxonomy to organize it. Globally, this architecture is guided by standards like ISO 14224. Under this standard, open-ended text fields are replaced with strict drop-down menus and standard failure codes, so the data can actually be aggregated and analyzed later. The asset hierarchy organizes equipment into a strict relational tree, cascading from site down to individual components. This structure ensures downtime data rolls up accurately from every component. You must separate this hierarchy from a PNID, as they serve different functions. The hierarchy dictates the data and reporting structure. The PNID maps the actual functional flow of fluids and gases through the physical plant. The final piece of this structural framework is Asset Criticality Ranking, or ACR. ACR flags equipment based on its direct consequence of failure. It systematically identifies which machines will cause immediate safety hazards or total production bottlenecks if they go offline. By enforcing strict hierarchies and accurate criticality rankings, you ensure that highly limited maintenance labor and expensive spare parts are directed exactly where they are needed most.
Not all assets fit neatly into a single building. Many industries manage continuous infrastructure networks, known as linear assets. You cannot track a 50-kilometer pipeline as a single discrete unit. Instead, it must be mapped out as a series of specific segments or nodes. Each length of pipe is logged with its own distinct GPS coordinates, its specific material composition, diameter, and exact date of installation. Utility networks follow the same logic. Electrical transmission lines are mapped segment by segment, tracking specific voltage capacities and individual structural towers across the grid. A rigorously designed asset register is flexible. It possesses the capability to map and track any physical topology, no matter how expansive the industry. The greatest threat to this system is human error. Over time, databases experience data drift, the inevitable decay of accuracy as physical reality outpaces digital records. When equipment is modified, relocated, or scrapped in the field, and those events aren't immediately logged, the register actively drifts away from reality. Consider an example from the heavy mining sector involving large-scale haul trucks. If 3 identical trucks are entered into the system by different technicians as CAT 793, CAT 793 haul, and 793 truck, it shatters the data structure. Because the system reads them as entirely different classes of equipment, it generates duplicate preventative maintenance schedules and corrupts the financial cost reporting. Or take a water utility, where engineers record the output for identical pumps using conflicting pressure units, PSI for one, kilopascals for another, and bar for a third. Analyzing performance trends across those pumps becomes impossible. These small inconsistencies compound rapidly. They leave dead ghost assets lingering on financial ledgers and directly break the accuracy of reliability models. Defeating data drift requires establishing strict master data governance policies from day one. Managing assets on basic spreadsheets creates systemic risk because they lack user access controls and provide zero audit trail for changes. On the physical layer, mitigation means affixing durable, scannable QR codes or RFID tags to every single piece of equipment in the plant. When field technicians scan those physical tags before beginning a repair, it guarantees that every labor hour and spare part is logged against the exact correct machine. On the digital side, you have to engineer the software to force data compliance. The system logic must require a mandatory check, asking, "Did asset information change?" before a technician is permitted to close out a work order. High-integrity data is maintained through hard-coded workflow integration, rather than manual administrative oversight. A standardized asset register provides the analytical foundation for advanced maintenance methodologies, like reliability-centered maintenance, or RCM. RCM is designed to mathematically optimize maintenance tasks by analyzing an asset's past failure history and its current operational criticality. But those complex RCM models will fail instantly if the underlying historical data feeding them is fragmented or corrupt. By aligning the register's architecture with the ISO 14224 data structure, organizations can take their localized failure data and accurately benchmark it against global industry peers. An uncorrupted, highly structured asset register is the non-negotiable prerequisite for graduating from reactive break-fix repairs to true proactive reliability. The value of this digital backbone extends far beyond the maintenance department. It serves as a unified reference point for the entire business. The exact same dataset is utilized by finance to calculate precise depreciation, by engineering to map plant expansions, and by operations to assess risk. This cross-functional alignment fulfills the core principles of the ISO 55000 standard for strategic asset management. By engineering and rigorously protecting a dynamic asset register, organizations eliminate operational silos, quantify their technical risks precisely, and drive genuine data-driven reductions in the total cost of ownership.